What's up, guys? Today we are doing mechanics, uh, A-level math paper, and it's from the year 2025. You guys gave a really crazy response on the 2025 paper one video, so I was like, man, I got to do a mechanics video as well. So let's get into it, and let's check out the first question. So it says that a crate is being pushed in a straight line along a horizontal surface by a force of magnitude 25 newtons, inclined at 20 degrees above the horizontal. The crate moves a distance of 12 meters in 8 seconds with a constant speed. So that's a lot to take in. You can just see right off the bat, they just throw so many different words at you. Let's break it down and understand what they're actually trying to say. So I'm actually just going to make some room over here. I'm going to go over here, and this is where I'm going to draw. So see, there's first of all, there's a horizontal surface, right? And on that horizontal surface, you essentially have a crate, and that crate is being pushed by a force. But the point is that force is being applied 25 newtons, inclined at 20 degrees above the horizontal. So let's say if I just draw a horizontal line over here, right? If I just draw a horizontal line over here, sort of like this, a horizontal line, then the force is basically being applied 20 degrees above the horizontal, right? It's inclining. You can see it's sort of like slant 20 degrees like that. And then that force is sort of pushing this block, right? It's pushing on the block, and they say the crate moves at a distance of 12 meters in 8 seconds. So 8 seconds later, basically, talk about this. 8 seconds later, the block will have covered 12 meters in distance, and with a constant speed. So there's acceleration. Acceleration is basically equal to 0. So what we can sort of see over here is they want us to find the constant speed of the crate. I'm just going to look at all of this one more time, understand if I'm not missing anything. And they say a crate is being pushed in a straight line along a horizontal, okay, by a force of 25 newtons, inclined at 20 degrees above the horizontal, okay. The crate moves a distance of 12 meters in 8 seconds with constant speed. Constant speed means no acceleration, and no acceleration means that the resultant force is equal to 0 in all directions. There is no resultant force acting on the block. That's the only situation when the speed is constant. Now they say find the constant speed of the crate. So the way we can sort of do that is we know the formula for speed. It's really simple. It's distance by time. And so what we sort of do is we put in the distance, which is right over here, 12 meters over 8 seconds. So we can sort of simplify this. I'm going to let the calculator do that for me. Not that good at mental calculations. So it's 1.5 meters, 1.5 meters per second. That's our speed, our constant speed. Okay, and then we sort of go down. It says B, find the work done by the 25 Newton force. Now, first of all, you need to know what work done even is. So work done is basically force times the distance. And one thing that has to be really, one thing that you have to be really careful about is that these two things, force and distance, they need to be parallel to each other. They need to be parallel to each other. It means they have to be in the same direction. And so if we sort of go up over here, you can sort of see that this 25 Newton force, does not do all of the work. Why? Because it's inclined sort of like this. Okay, it's sort of like inclined. So the block, if this is the block, let's say this is the block, and there's a force that's inclined right over here. So technically, this block is not moving in the direction of the force, is it? The direction of the force is in that direction. The block isn't moving there. Instead, the block is moving horizontally in a straight line. That's what they tell you in the question. So that means that this 25 newtons of force is not doing all of the work. Or it is doing all of the work, but that's not the work they want us to tell them. They want us to tell them, yes, they want us to tell them the work done by this force. And so what I'm saying in a different way is that if you have a block and it's being pulled like such, it's being pulled in that direction. If it's not going in that direction, then not all components of that force are doing work. So what do I mean by that? What I mean by that is that this force is going to have two components, a vertical component and a horizontal component. Now the vertical component does no work whatsoever. Why? Because the block isn't moving up or down. So yes, there is a force in the vertical direction, but there's no distance being covered in the vertical direction. So distance is 0 in the vertical direction. So work done in the vertical direction is equal to force in the vertical direction multiplied by the distance in the vertical direction. Distance is 0, so work done is just going to be 0. But this horizontal component does do some work, and this is basically going to be 25 cosine 20. So I did some trigonometry over here. You can sort of make this triangle, and you will realize why this is 25 cosine 20. But yes, this 25 cosine 20, this horizontal component of the 25 Newton force, that does do work. It's doing work. But why? Because the block is traveling in the horizontal direction as well. So we go down over here and we answer this question for them. So the force in the horizontal direction is going to be 25 cosine 20 multiplied by the distance. So what is the total distance that the block covers? Well, it covers 12 meters. 12 meters. We don't have to write meters for now. It covers 12, and then we can sort of solve this on our calculator. Let's get this bad boy in the degree mode. It's 25 cosine 20 times 12, and that is 281.9. So that is going to be 281.9 joules. Why? Because work done and energy are in joules. Okay. So we go over there to part C, and they say find the power at which the 25 Newton force is working. What is power? Power is work done or energy transferred per unit time. So we already found the work done. That's 281.9 joules. Now the power is just going to be the work done divided by the time taken, and the time taken was 8 seconds, right? It took the block 8 seconds to travel that 12-meter distance. So this is simply just going to be 35.24 watts, or just 35.2 35.2 watts. That's the unit of power. So now we move over to the second question, and says two particles P and Q of masses 0.2 kilograms and 0.1 kilograms respectively are free to move in a straight line on a smooth horizontal plane. Then they say P is projected towards Q with a speed 5 meters per second, and at that same time, when P is projected, they project Q in the direction away from P with a speed of 2 meters per second. And they say when P collides with Q, they coalesce. Coalesce means when two things hit each other and they join together. So they ask us find the kinetic energy lost during the collision. So I'll explain the question to you first. Essentially, what's happening is you have two particles P and Q. So this is Q, this is P. Now what they do is basically Q is some distance away from P. And you're like, well, how do you know that? They didn't say that in the question. Well, if you go and read the question, they say P is projected towards Q. So if something's far away from you, only then can you project something towards it, right? If we're just standing close to each other, like you cannot project yourself to me. You're already standing right next to me. So for something to be projected at another thing, it's must that one thing has to sort of be away from the other. So Q is already some distance away from P. And then what they do is that they basically launch these both particles at the same time. So this guy goes at 2 meters per second, and they launch this guy at 5 meters per second. And so what happens is after some time, these guys basically, they're going to join each other. And the reason for that is because Q has less speed than P. So it's like this guy is trying to run, but this guy is faster. So eventually he's just going to catch up to him. So what's happening is that when this guy catches up to this guy, they're going to join and form a new particle. Now this particle, let's call that particle, call it particle K. Right? Let's call this new particle K. This is when they coalesce. Coalesce means join. This particle is going to have a mass m of, well, the mass of the first particle, 0.2, and the mass of the second particle is 0.1. So you add them together, this new particle is going to have a mass of 0.3 kilograms. And it's going to have some speed, right? And it's going to have some speed too. Let's call it velocity v. We don't know what that speed is. And what they want us to find is the kinetic energy that's lost when they sort of coalesce and collide with each other. So how do we approach a question like this? Well, see, if you want to, I'll explain it to you guys in this way. So if you want to find the kinetic energy lost, what you're really looking for is you're looking for the change in the kinetic energy, because that's what energy lost is. It's what was the, so change in kinetic energy is basically going to be, now this change is going to be a negative quantity because it's a loss, right? The kinetic energy is going to be lost. So it's going to be the kinetic energy final minus the kinetic energy initial. So what happens is, see, when two things collide, obviously they release sound. Obviously, there's some sort of heat interactions. So energy, the kinetic energy that the system initially had, some of it gets lost to sound, heat, friction, other things. So when these two particles collide, they sort of have all of those interactions. So you may hear a sound. So kinetic energy has been converted to sound. So there's going to be a loss. There's going to be a decrease in kinetic energy. That's why they say find the loss in kinetic energy, because they're hitting each other, they're making sounds, they're losing energy in some way. Okay, what about momentum? Before I go on to momentum, I'll show you guys how you do a question like this. So this is going to be 1/2 mv squared initial, right? Sorry, final. And then this is going to be 1/2 mv squared initial. Now see this this initial term and this final term, they're not talking about one individual particle. They're not talking about P or Q or K. They're talking about the entire system. So what you're going to do is you're going to take the entire system, you're going to look at the entire system, observe what was the kinetic energy of the entire system before the collision, observe what was the kinetic energy of the system after the collision. So this initial quantity, this initial quantity, if you look at the system initially, which is this guy over here, the system basically comprises of two particles, P and Q. So the initial kinetic energy, the total initial kinetic energy, depends on two individual particles. You're going to add them up, and then you're going to get the total initial kinetic energy of the system. Okay, so it's going to be the initial kinetic energy of P plus the initial kinetic energy of Q. It's going to be the initial kinetic energy of P plus the initial kinetic energy of Q. And then this guy is basically the system in its final state has this one particle, which we're calling K, and its kinetic energy depends on just this one particle, because you have this system, and inside that system there only exists one particle. So it's going to be the kinetic energy of particle K. Now see, thing is, to find this and to find this, you are given all of the information. So the formula of kinetic energy is 1/2 mv squared, right? You have the mass of this guy, you have the initial velocity v for this guy, then you have the mass for this guy, you have the initial velocity v for this guy. You do know the mass for this guy, but you don't know the velocity for this guy. So the only thing you're supposed to find is somehow the velocity. So the question is, well, how do I find velocity? Well, whenever you have an initial state and a final state, and there's this thing called collision involved. What I want you guys to automatically think about is momentum. Momentum. And initial momentum is conserved. So the momentum of the system that you have initially, you will have exactly the same amount of momentum after that collision. Okay? And so what I mean by that is, well, the momentum before collision, so momentum is represented by the letter P. So momentum before collision, and I'm going to represent collision by this explosion thingy, equals momentum after collision. After collision. So what we're looking for is we're looking for the momentum of the system before it collides. And then once we have that value, we can put that equal to the momentum of the system after the collision. So momentum, so the first, this I'm going to do this for the momentum before collision, so I'm going to put a 1 over here. So this is the total momentum of the system before the collision. It's going to be equal to the momentum of P plus the momentum of Q. So that's just going to be mv, and this is going, because that's the formula of momentum, right? This is the momentum of particle P, and then this is the momentum of particle Q. And this, once we find this P, we can sort of take it over there to the momentum equation for after the collision, and that's just going to be mv, but this time it depends just on one particle, particle k. So that's the plan. From this equation, what we're going to have is we're going to know the momentum, we're going to know the mass, because we do know the mass of particle k. We're going to use this equation to find the velocity, and we're going to chuck that velocity in there. So that's the plan. Now let's do it real quick. So the momentum before collision is just going to be 0.2, which I believe is the mass of particle P. Yes, that is the mass of particle P. And particle P has a speed of 5. And then you have a mass of 0.1, and then the speed of particle Q is 2. So you can do this, and you will basically find out. So it's 0.2 times 5, and then plus, sorry, that was 0.2, 0.2 multiplied by 5. And then we are going to have 0.1 multiplied by 2. So the total momentum before collision is equal to 1.2 kg meters per second. That's the unit of momentum. And then the same momentum will be conserved to after the collision. So then after the collision, it's going to be P equals mv, and this is the momentum of k. And then this momentum, see, the momentum you have initially, that has to be conserved. It's going to be 1.2 equals mass of k, which we found out was 0.3, and then the velocity of k is what we're trying to find out. So when we solve this, this is just going to be 1 by 2 divided by 0.3, and I think this is going to be 4. Yes. This is 4 meters per second, because that's the unit of speed. And then what we can sort of do is now we have the velocity of speed. Now we can go and put it into the energy equation. So it's just going to be the Ke final. Let's find that out. So the Ke final is equal to 1 by 2 mass of K, which is 0.3, velocity of K, which is 4, square that. So that's going to be equal to 4 times 4 times 0.5, and then times 0.3. So that's going to be 2.4 joules. Because kinetic energy, any energy is in joules. And then we find the kinetic energy initially. So that's just going to be 1 by 2, 0.2 times 5 squared, plus 1 by 2, 0.1 times 2 squared. Let's solve this out. This is going to be 0.5 times 0.2 times 5 squared. Sorry, that is not 0.2. So that is equal to 2.5, and then we add into it 0.5 times 0.1 times 2 squared. Okay, and then we sort of close the bracket on this, and we get 2.7. We get 2.7 joules. And so when we check out the energy change, so the change in Ke, that's just going to be the final kinetic energy, which is 2.4 joules, minus the initial kinetic energy, which is 2.7 joules. And so the answer is going to be a negative number. It's going to be negative 0.3 joules. So this negative, basically, this guy basically tells us that energy has been lost. Okay, if this was a positive sign, that would have meant that energy has been gained. Now we got question 3 going on over here, and it says a particle P of mass m is attached to one end of a light, inextensible string of length 2.6 meters. Okay, then they say the other end of the string is attached to a fixed point on a horizontal ceiling, so that they're talking about this point right over here. And then they say that the string is taut. So what does that mean, that a string is taut? It means that it's not loose, it's fully stretched. Then they say the particle is held in equilibrium by a force of magnitude 35 newtons. Okay, this equilibrium part is really important. So equilibrium basically means that the resultant forces are equal to 0. In any direction, there's no resultant force acting on this particle. That is going to be really useful in just a second. This equilibrium part is going to be what solves this entire problem. That's it. Then they say a bunch of other stuff like acting in the vertical plane, which is perpendicular, blah, blah, blah. We can see that in the diagram. So I don't think I have to sort of read this, because they've already drawn this thing for perpendicular, that I can see that they're perpendicular. They say the tension in the string is T, so that's what they're calling it. The tension in the string is T. The vertical distance of T from the ceiling is 2.4 meters. So this thing right here is 2.4 meters, which is also this thing right over here. Right, and what I'm supposed to do is I'm supposed to find the value of m, and I'm supposed to find the value of t. So how do I do this? What's my plan for this question? So well, this is where you sort of, this thing right over here, this is what is going to solve this entire question for you. So equilibrium means forces are the resultant the resultant of forces is 0 in any direction. That's what it means. That's what equilibrium means. We're going to use that idea, and we're going to do something over here. So first of all, let me just draw a free body diagram for this point P. So first of all, I know this point P has a tension in that direction, because tension always acts away from the point of interest. In this case, the point of interest is P. So the tension is sort of acting away from P. If you were looking at this with the respect of, let's say, this point right over here, this point, then the tension for this point would be in that direction. It's like tug of war. In tug of war, both sides are being pulled, but each side feels the pull in the opposite force, not in the side where they're pulling the rope, right? So it's the same over here. So if we look at point P, the tension is sort of in that direction. That's where T is. That's one of the forces. The 35 Newton force is another force. I'm actually going to draw it out over here. So that's particle P. It has one force, which is the tension, acting sort of like that. It has a force of 35 newtons. 35 newtons acting like that. That's 35 newtons. And then it has its weight acting downwards like that. So this guy is basically mg. Okay. This guy is tension T, and then that guy right there is 35 newtons. Once you've drawn the free body, you go back to that equilibrium idea, and it tells you when particles or anything is in equilibrium, it has no resultant force acting in any direction onto it whatsoever. So what I can sort of do is I can break this T into its vertical component, and its horizontal component. So this will be Ty, this will be Tx. And so once I've broken T down, I don't really need that diagonal component anymore. And then what I can sort of do is I can do the same thing with the 35 Newton force. I can break it down into its vertical component. So this will be 35y. And I can break it down into its horizontal component, which is going to be 35x. Okay, that's the horizontal component. And then I don't need this diagonal force anymore. Now you can see it's really, really simple. Why? Because, well, you can assign directions. You can say up is positive, so that means down is going to be negative. And you can say that right is positive, which means that left is going to be negative. Or even better. Or actually, you know what? Let's let this stay. I'm going to stay with this. So up is positive. So, and then right is positive. So for the vertical direction, we've assigned that the upwards direction is going to be positive, and for the horizontal direction, we've assigned that the right direction is going to be positive. That means that the left direction is going to be negative. Now what we're going to do over here is we're going to say that if I add all of these guys up, so if I add all of the forces in the vertical direction, which is these two guys and this guy, I should get 0 as my result. There should be no resultant force. That's what equilibrium means. If there is a resultant force in any direction, I don't get 0, then that means that I need to have acceleration due to that resultant force, right? Resultant force is equal to mass times acceleration, Newton's second law. If it's in equilibrium, all the forces need to be balanced. So in the vertical direction, all of these forces are going to add up to give me 0. And then the same thing is going to happen in the horizontal direction. This force and this force, they're going to add up to give me 0. And you're like, well, okay, that's interesting, but how does that find me m and t? How does that find me m and t? It's going to make sense in just a second. So let's first do this, okay? It's really weird that to find m and t, you're actually using equilibrium, making components out here. Like, it's crazy, but just in a second, it's going to make sense how you can find m and t using this method. So we've done this. Now see, to actually separate out the components, what's important that you have some angles over here. So we have this shape, right? This thing over here. So we need to have some angles, because without angles, you cannot really break diagonal forces down into its components. So if I complete this as my triangle, if I sort of complete this as my triangle, I have this. I know what this is. This length is 2.4. So I'm now doing some trigonometry. This is not physics now. I'm doing some trigonometry. This is 2.4, and this is 2.6. So I can use these two guys to find out this angle. And then I know this is tension. So I can, once I have that angle, I can sort of do something with the tension. I can break it down into its components, given that angle. For this 35 Newton force, I believe one thing that I can sort of do is I sort of have to figure out either this angle over here or that angle over there. This I know is 90 degrees. So I'm trying to think of something that I could do. How will I find another angle? Okay, I have an idea. So this is going to be 90 as well. If I can find out this angle, and I know this angle is 90, then what I can do is I can sort of add these two up, subtract them from 180, and I'll get this guy right over here, this guy, right? And then I know that this entire angle is 90 degrees, so when I subtract that guy from 180, I'm going to get this guy. And then I can add this guy and that guy, subtract them from 180, and I'll actually no, I don't even have to do that. If I can get this angle, if I can get this angle, so I'm going to erase this stuff. Oops, if I can get this angle right over here, then I basically have a triangle. I'll know an angle. I know a side. I can do some trigonometry, break this force down into its components. So right now, I'm just going to do some trigonometry. And remember, what we're trying to do is we're trying to break the forces into their components. So let's do that. Let's find out this angle right off the bat. We know that this thing is equal to 2.4 meters. 2.4 meters. So we got this, and we got this, and we got that angle. So what do we use over here? This is the hypotenuse. That is the perpendicular. So we're going to use sine. So we are going to use sine. Sorry, this is going to be sine theta equals so this is going to be sine theta equals 2.4 over 2.6, right? Perpendicular over hypotenuse. And so what I can do is I can get my angle from here, but I don't really have to, because I have another idea. But I'm 2.4 divided by 2.6. I'm actually not going to do that. I'm actually not. You can find this angle out. Okay, you know what? I'm not going to find this angle out. You guys can go and find this angle out if you want to. I'm personally not doing that. I have another idea that's going to solve this question much faster. I'm going to find this base right over here. This base. That's what I'm going to do. That base is going to be So it's going to be, I'm going to use the Pythagoras theorem over here. So it's going to be under root 2.6. Now this is hypotenuse squared equals sum of the square of the other two sides. I'm using that. You can use it and find that base. So it's going to be this thing. It's going to be 1. That base is equal to 1. That thing is equal to 1. And so cosine theta is going to be 1 over 2.6. Okay? 1 over 2.6 base over hypotenuse. Sure. Now this can sort of allow me to basically break down my tension into two components. The vertical component, which is going to be like this, and then the horizontal component, which is going to be like this. So this, I know the tension is T, right? So then the horizontal component, then Ty is going to be, you can use that trigonometry again, you know, this angle is theta. Its tension in the vertical direction is just going to be sine, wait, I'll have to sort of think about what it's going to be. So it's sine theta is equal to base over, so sine theta over T vertical, which is the opposite of theta over the hypotenuse, which is T. So yes, so Ty is just going to be T sine theta, and then Tx is going to be T cosine theta. Now you can sort of go ahead, sort of figure out how I did this, do the trigonometry. I've done these questions a lot of times, so I know what Ty and Tx are going to be. If you don't understand that, you can go ahead and do some trigonometry. So that's my components of the tension T was a diagonal force. I've broken it down into its vertical part and its horizontal part. Now what I'm going to do is I'm going to do the same for that 35 Newton force right there. So what I'm trying to do is I'm trying to find, if I complete this triangle, I know that this is going to be 90. What I'm trying to find out is this angle right over here. And the way I do that is I know what theta is. So so theta is actually going to be, if you can use this to find theta. So theta is going to be sine inverse 2.4 divided by 2.6. So this is what theta is, right? This is what this guy is. So this guy is theta, this guy is 90. You can add these guys up, and then you can subtract them from 180. Right? So you're going to get this thing, which is 22.61. And so this is this angle right over here. Now you know that this entire angle is 90 degrees. So when you minus this guy from 90 degrees, you're going to get this guy. So 90 degrees minus this guy. That's going to give us 67.380. So this angle, this angle over here, this is sort of also equal to theta. So theta was 67.380, and then this angle is also 67.830. So we can say that this angle is also, just simply put, it's theta. So what we can do is we can basically, for the 35 Newton force, we can write its vertical component and we can write its horizontal component. So we already know what sine theta and cosine theta are because we've already found them. We've already found what the sine is for theta. It's this fraction, and we've already found out what the cosine is for theta. It's this fraction right over here. So what we can sort of do right now is we can sort of understand that this force, this 35 Newton force, it's sort of going to break down into its vertical component like this and its horizontal component like this. And this is theta over here, right? So what is going to be the vertical component? It's going to be, so if I draw a triangle out for you, this is theta. This is going to be the vertical component of the 35 Newton force. So it's just going to be cosine of this 35 Newton force. It's going to be 35 cosine theta. And then the horizontal component is going to be this guy. So that's going to be 35 sine of theta. Right now, I've just done some trigonometry over here. You can pause the video, do it on your own if you don't understand what I just did. So technically what we've done is now we're on this stage right over here. We've broken it down into the vertical components, the horizontal components, and now we just have this, we just have this thing over here. So what is it that we initially said? We said that up is positive, and this is for the vertical direction, right? This is for the vertical. And for the horizontal, we said that right is positive. So we've broken everything down. Again, we're simply using that equilibrium idea. So we had forces. We know that the resultant is going to be 0. So we broke all of the forces down. And now what we're going to do is now we're going to apply that equilibrium rule. We're going to say that the sum of forces vertically is equal to 0. So we're going to sum all of the forces up now. So the first force, the second force, and the third force, all of them have to equal 0. So what is the first force? Now, it could be any force. You can take any force. So the possible vertical forces are Ty, which is the vertical component of tension, 35y, which is the vertical component of the 35 Newton force, and then mg, which is the weight of the particle. So let's put Ty in here. Ty. Now, is Ty pointing upwards or is it pointing downwards? So it's pointing upwards, so it's going to have a positive sign. Then I have the 35y force, this guy, which I know what it's 35y. Is this guy pointing upwards or is it pointing downwards? It's pointing upwards, so it's going to be positive. And lastly, I have the weight. Is the weight pointing upwards or downwards? It's pointing downwards, so it's going to be negative. Now what I'm going to do is I'm going to simplify this, and instead of writing Ty, 35y, I'm going to write the values I found for them. So this is 35y, this is Ty. I'm going to write T sine theta plus 35 cosine theta minus mg equals 0. Okay? And so all of this sort of has to add up to 0. That's my first equation. This right here is my first equation. Now what I want you to see is realize how many unknowns I have in this equation. So I have T as my unknown. So this T is an unknown. and the mass m is an unknown. All of the other things are known. We know what sine theta is, it's this guy. We know what cosine theta is, it's this guy. We know what 35 is 35, so it's already known. We know what g is. G is the gravitational acceleration. It's 9.81, or in other words, 10 meters per second squared. So everything else is known. We have one equation but two unknowns. You cannot solve that. You need to have one equation and one unknown. You can solve that equation. So we cannot solve this equation. What do? Forget about this. We still follow that equilibrium idea. Sum of forces horizontally. Sum of forces horizontally. Horizontally is also going to be 0 because they're in equilibrium, right? So that's 0. How many forces do we have horizontally? We have two forces, 35x and the tension x. So we have 35x. We got two forces, this guy and this guy, and they both should add up to 0. So it's going to be 35x and it's going to be tx. Now where is tx pointing? Where is the horizontal component of tension pointing? It's pointing to the left. And we said that left forces are going to be negative, so we put a negative sign next to it. And then right is positive, so we put a positive sign right there. Now it doesn't matter if you select down to be positive, you're still going to get the same answer. Or if you select left to be positive, it's still going to be the right answer. The positive negatives are completely up to you. So I'm going to simplify this. So tx is just t cosine theta. This is going to have a negative sign. And then that 35x is going to have the 35x is 35 sine theta, and they're equal to 0. So how many unknowns does this equation have? This equation has t as your unknown, and nothing else is unknown. So you can solve this equation. This is your equation 2. You can solve this equation for t, and you will find out what the tension is. Now, before I even do anything, I'd like to answer that initial question of how does thinking about equilibrium find the value of m and find the value of t. Well, it helps us to now find the value of m and t, because look, we have the second equation, and what we can do from that is we can find the value of t, and then we have the first equation, which has two unknowns, but we can use second equation to find t, and then we can put that value of t into the first equation, and then the only thing that'll be unknown is going to be the mass. And so we can solve for the mass, and we can find the value of the mass. So at the end of the day, we use this idea of equilibrium, meaning resultant force equaling out to 0, and that is going to allow us to find the value of m and find the value of t. So let's solve this out. So I can send this guy over there to that side of the equal sign, and then I can say that t cosine theta is equal to 35 sine theta. And what is cosine theta? Well, cosine theta is basically 1 over 2.6. So it's 1 over 2.6, which is just going to be t over 2.6. And then 35 sine theta is basically 2.4 over 2.6. So this is 2.4 over 2.6. And so if I make t the subject, it's just going to be t is equal to 2.6 times 35 times 2.4 over 2.6. And I solve this out, and it's going to give me 2.6 times 35 times 2.4 over 2.6. Right? I solve this out, and it gives me 84. So that is the value for my tension. Okay, and then now since I have my tension, I can go ahead, plug that into that equation. So that's going to be 84. What is sine theta? Sine theta is 2.4 over 2.6. And then I have plus 35 cosine theta. So cosine theta, again, it's just equal to 1 over 2.6, and then minus mg equals 0. So I can send mg over here to this side of the equation. So this is going to be mg, and then I can solve all of this out, put that in here. So that's going to be 84, 2.4 over 2.6, and then plus 35, 1 over 2.6. Okay, so I solve all of this out, and I get 91. And so mass, now I can divide this g over there to the other side. So the value of g is 9.81, and 91 divided by 9.81, that's going to give me 9.28. That's 9.28 kilograms for mass. So that's your question. Now, how do you solve questions like these where particles are in equilibrium? Well, buddy, that equilibrium word is the key to solving problems like these. You just have to make equations where they're going to add up and give you 0, and you have to make those equations for both the vertical direction and the horizontal direction. Once you do that, the question is going to answer itself. We got question 4 over here, and it says a car is traveling along a straight horizontal road. Then they say the car passes through a point A on the road, traveling at a speed of 15 meters per second, and then accelerates uniformly at 0.4 meters per second squared for 30 seconds. Okay, so basically, we got a car, and you got, like, let's say the car is, so let's imagine a straight road like this, and then let's say this is point A. So the car passes this point A at 15 meters per second of speed. Okay, and then they say that it sort of accelerates after it passes point A. So after it passes point A, now it's accelerating, right? And it accelerates till like 30 seconds have passed. So let's say it passes A at t equals 0, time equals 0. Then till t equals 30, it's going to be accelerating. Okay, and then it's going to reach some speed. We don't know what that is, but we can find that out right now. We don't have to. And then they say the car then moves at a constant speed. So it accelerates till t equals 30, and then it starts to move with whatever speed it finally got at the end of that t equals 30. So it moves with that speed for 3 t seconds, where t is smaller than 30. So t is smaller than 30. Okay, so t is some amount of time, and it's basically it moves for 3 t seconds at a constant speed. Okay, and so after this 3t has passed, we will be onto some new time, which we can call 30 plus 3t. So 30 was this guy, and then we traveled for 3t. So the final time is going to be 30 plus 3t. And then it says the car decelerates uniformly. Then the car decelerates uniformly at 0.2 meters per second after a further t-second pass, and then it gets onto some point B. So after this time, it's gonna after this time, this final time, it decelerates. So it decelerates this time for t more seconds, for t seconds, and then the final time that we're gonna have is going to be 30 plus 3t, and in this time we have to add t more seconds. So that's just going to be 30 plus 4t seconds. It's the final time is going to be 30 plus 4t seconds. And they say what we have to do is we sort of have to, on the given axes, sketch a velocity time graph for the motion of the car between points A and B. Okay, so I suppose then A is supposed to be our final point, and B is supposed to be, sorry, A is supposed to be our initial point, and B is supposed to be our final point. So what we sort of have is we've got V over here on the velocity axis, and then we got T over here on the time axis. And so what we sort of have to do is we're sort of just going to start plotting our graph over here. So what we can sort of do is we can sort of make a table to help us out over here, and that table is going to look something like this. So we're going to have our velocity over here, and we're going to have our time over here. So velocity, so or actually, let's have the time over here and velocity over here. So at time 0, t equals 0, that's when we cross A. So the velocity at that point is 15 meters per second. And then at when time equals 30 seconds, we are going to have some velocity, which we don't know what that is going to be, but we can sort of calculate that because we can use the formula velocity equals u plus at. And using this, well, we sort of know that we need to find the velocity when the initial velocity was 15 meters per second. Actually, I'm not even going to write the units right now. Let's not write the units right now. And then plus, so it accelerates, right? This is the first part from A to this 30 seconds. It accelerates in this region, and it accelerates with an acceleration of 0.4 meters per second. So we can put that in the formula, 0.4. And then the time was 30 seconds. So all of this is going to solve out to give us 15 plus 0.4 times 30. So this is going to be 27 meters per second. So this is 27. And then when time is equal to 30 plus 3t, okay, that's sort of this part, 30 plus 3t, it's still traveling at 27 meters per second. The reason for that is because, well, from this, if I go back to that diagram up there, and you can sort of see that from t equals 30 to t equals 30 plus 3t, and that's the part where we travel with constant speed. Okay, so we can see that from this guy, from 3t seconds, from 30 seconds to 3t seconds, we traveled at constant speed. So it's not going to change. It's going to be 27, and then we sort of decrease at the end. So when time equals 30 plus 40 seconds, we have some velocity, which we don't know what that is, but we can again calculate that out. So we can again use the same formula, v equals u plus at. And what we can sort of see is that from at the final instant, from this point, I'm just going to make some space over here. So from this point, 30 plus 3t till the last point, 30 plus 40, we decelerate, and we decelerate, and we can see that deceleration is given to us right down here. It's given to us at 0.2 meters per second squared. So what we can sort of do is we can again find the final velocity, which is going to be at the point 30 plus 40. We can find that by saying that u was basically u is equal to 0.2, and then at is going to be a is negative 0.2, the negative sign because it's decelerating, and the time it took was basically a capital T seconds. Capital T, that's what you can go over here and check out in the question. It took t seconds. So this is going to be a really weird number. It's going to be 0.2 minus 0.2t. Okay, and then we do know that t is less than 30 because they told us that in the question. So we don't know what the final speed is going to be, but it's in terms of t, it's basically going to be 0.2 minus 0.2t, which I'm really surprised because it's a really weird thing to have. But anyways, we can start plotting out this graph. So we can put a point over here, and this is the first point. So this is point A. All of this is point A. The time is 0. Velocity is 15. So velocity is 15 over here. And then velocity, we go sort of over here. We sort of accelerate. We sort of accelerate till 30 seconds. So we can say this right here is going to be till 30 seconds. And the velocity, we reach the velocity at this point is basically, see, we're on point number 2 now. The velocity is 27. And then for some amount of time, we sort of move at constant speed. And we have time over here. Time is going to be 30 plus 3t. So I'm going to sort of rub all of this stuff out over here. Okay, so this is 30 plus 3t. Okay, and that's a straight line because we're moving at constant speed. Okay, so we from this to this, we basically took a time of 3t seconds, so we just add 3t into 30 to get our final time right over here. Okay, and then what we can sort of do is we can sort of draw our next point. We've drawn our first point, our second point, our third point. Now we can draw our last point. So we can sort of draw it somewhere around here. I don't know what it's going to be, so I'll just put like a random dot over here. Like, let's say somewhere over, I'm trying to see, let's say somewhere over here. We can just put a random dot because we don't right now know what the value is of b. Okay, so it's going to sort of do something. Oops. Sort of do something. Oops. I'm going to draw this out properly again. It's going to do something like that. So that's this final point is going to be our point B, and over here we have our time as 30 plus 4t, and we don't know what the velocity is at that point. I mean, we do know, but the velocity at this final point B, this is basically 0.2 minus 0.2t. Oh, actually, my bad. I made a mistake. I made a crucial mistake. This was the initial velocity. So if, see, this is point B, our final point, and this it was our first point from which we were sort of coming down to point B. Our velocity at this point was 27, and so at this point, at point B, it has to be 27 minus 2t. My bad, I'm so sorry for that. It has to be 27 minus 2t. Okay. Okay, now we're sort of doing okay. So it's 27 minus 2t, and we are yet to find what this is. We don't have the value for t, so we cannot find this as of now. Okay, we've sketched out the graph. I think that's what we were supposed to do, so we can move on to the next part. And it says the distance from A to B is 2,750 meters. Find the value of t. Okay, so the distance basically means that all of this part the area under this entire curve or this graph, all of this area plus all of this area plus all of this area, we can find that and add that up, and that is essentially going to be equal to this thing right over here, 2,750 meters. And then they say find the value of t. So what we're supposed to do is we're supposed to make an equation of this area to the first area, the second area, the third area, add them up, put them equal to this guy, and then sort of by doing that we will somehow find the value of t. Okay, I don't know how that's going to happen, but that's what the question is telling us to do. So let's try that out. So distance from for the first section, let's call these sections section 1, section 2, section 3. So the area under the first section, so we can see that looks sort of like a trapezium. This thing looks like a trapezium. I draw a line over here. You can sort of see this thing looks like this, like this, like this, like this. That's like a trapezium. So we know the formula of a trapezium. It's basically 1 by 2 times side 1 plus side 2. So side 1 is 15, side 2 is 27, right? And then multiplied by height, and the height is going to be 30 seconds. Okay. So again, I will draw the trapezium out for you like such. And so this guy right here is the height. This is 30. This guy is the side 1, which is 15. This guy's side 2, which is 27. I hope that makes sense. Okay. And then we're supposed to add in the second area. So that second section looks like a triangle, sorry, a rectangle. So we can sort of just do length times breadth. So that's just going to be 27 times this section, this section, and this essentially, if this section equal to a time of 3t, right? Because again, if you don't believe me, you can say, well, this is the final time, this was the initial time, so you can do 30 plus 3t minus 30. This is the final time minus the initial time. This will cancel out with this, and so the time it took for section 2 is going to be 3t. So that's going to be the base. So 27 times 3t, and then for the final section, we can sort of see that it's also a trapezium. So what we can sort of do is we can sort of again apply the formula of trapezium 1 by 2. Side 1 times side 2. I think this is going to take more space, so we can sort of go down over here. So this is plus, this is 1 by 2. Side 1, so side 1 is basically going to be, so this is side 1. This is 27, so if I draw this out like this, sort of something like this, then this guy is 27. Okay, this guy is going to be 27 minus 0.2t. Okay, because the velocity at this point is this guy, 27 minus 0.2t. So it's going to be that, and then this base, if you can sort of see this part over here. This base is the time it took for this interval was t seconds. And if you don't believe me, you can sort of, well, you can take this final time, subtract it from the initial time. What's going to happen is that the 30 is going to cancel out the 30, and then the 4t, when you subtract 3t from 4t, you're just going to be left with a t. So the t is going to be the base. It's going to be 1 by 2 times side 1, which is 27, plus side 2, which is 27 minus 0.2t, and then times the height, which is going to be t. And all of this has to equal to 2750 meters. Okay, so let's put this in our calculator and sort of solve this out. So this is going to be 0.5 times 15 plus 27 times 30. So that is going to be 630. So the first area is going to be 630. And then add the second area. So that's just going to be 27 multiplied by 3t. 27 multiplied by 3t. So that's going to be 81t. And then the final area is going to be, sort of do that. So that's going to be, 27 plus 27 is going to be 54. So this is going to simplify to 54 minus 0.2t. Okay, and then what we can sort of do is we can sort of say that this 54 divided by 54 divided by 2 is going to be 27. So this is going to be 27t minus, so 0.2 divided by 2, that's going to be 0.1. It's going to be 0.1t squared is equal to 2750. Okay, so we can simplify this out. This is going to be 630 plus 81t plus 27t minus 0.1t squared equals 2750. Looks like a quadratic equation. We can solve these two guys out. It's going to be 630. So 81 plus 27, let's see what that is. 81 plus 27, that's going to be 108t. And then plus, oh, sorry, it's minus. So it's minus 0.1t squared equals 2750. We can take this 2750 to the other side of the equation. And so we'll simply be left with 0.1t squared. Hold on. 0.1t squared plus 108t. And then we can subtract from 360, we can subtract 2750. So that's going to be negative 2120. Negative 2120 is equal to 0. And now what we can sort of do is one thing we can do is we can multiply this entire equation by negative 1. And what that's going to do is that's basically going to get rid of this negative sign over here. When I do that, I mean, you don't necessarily have to do that, but I'm just going to multiply the entire equation by negative 1. It's going to be positive 0.1 t squared plus 108 t. Sorry, these signs are going to change as well. It's going to be negative 108t, and then positive 2120 is equal to 0. Okay, and then what you can sort of see is that it looks like a quadratic equation. It has a t squared, it has a t term, and it has a constant term. So what we can simply do is we can apply the quadratic formula. So that's just minus b plus minus under root b squared minus 4ac over 2a. And so that's just going to be, minus b is just going to be positive 108, and then plus minus under root b squared, so that's going to be 108 squared, minus 4 times 0.1 times 2120 divided by 2 times 0.1. So let's solve all of this out. We got 108 plus minus 108 squared minus 4 times 0.1 times 2120 divided by 2 times 0.1. So we solve all of this out. We get 1060. So we get t equals 1060. And the other answer that we're going to get is when we change that sign to negative. So let's do that. negative. That's going to be 20. T equals 20. Now, which answer do you have to go with? Do you have to go with 1060 or do you have to go with 20? And see, for that, you sort of go up over here to the question. And initially, the question told you that the time is less than 30 seconds. So that means that we cannot go with this 1060 as our answer, but instead we have to go with this guy as our answer. Okay, so now I think that's what we were supposed to do with part B. Yes, we did need to find the value of t. We've done that. We can go on to part C. And it says the car continues its journey from B, decelerating uniformly at 0.5 meters per second squared until it comes to rest at point C on the road. And we're supposed to find the total distance from A to C. Okay, so we can sort of go up to the graph. We don't really necessarily need to, but we can go up to the graph. And so see, from point B, sort of move on. I can erase all of this stuff. Make some room over here. Okay, and what's essentially happening is from this point B, we now decelerate. Point C. We now decelerate to point C. So this, we can call this our point C. And do they give us the time for which we decelerate? How long do we decelerate for? Okay, so we decelerate until we come to rest. Okay, so our final velocity over here at this point is going to be 0. At point C, the velocity is going to be 0. And this is our final point. And so see, we already know the distance from point A. So this was point A, this is point B. We already know this entire distance. That's what they tell us. In the question, they said that this entire distance is 2750 meters. So what we're supposed to do is we're now just supposed to find the distance it's going to take for this final part, and then we can add that into this distance, and so we will have our distance from part A to part C. So how do we sort of do that? How do we sort of find the distance from part B to part C? Because we know the distance from part A to B. How do we find the distance from part B to C? We know this is 2750. How do we find distance from part B to C? Well, one way of doing that is by using your equations of motion. You can sort of use this equation 2as equals v squared minus u squared. Why can you do that? Well, because you have acceleration. It's not acceleration, it's deceleration. You know that it's 0.5 meters per second squared. You know the final velocity. The final velocity, rest means the final velocity has to be 0. And you can find that initial velocity. And I'll tell you guys how you can find that. But then what's going to be left in this equation is just this, it's just going to be this s term right over here. And that s is basically, it's going to tell you the distance from B to C. And so you can sort of make that the subject. Everything else is known. You have one equation, one unknown. You can solve this equation. Now, how do I find that initial velocity? How do I do that? Well, it's simple. At B, the velocity, the equation for velocity, I'm going to write velocity at B. So velocity at B, we already found an equation for that. You can go up over here. And the equation for that was basically this guy. The velocity at B was basically equal to this guy. It was 27 minus 0.2 t. It was 27, and see, we know the value of t now. It's 20. We can say it's 27 minus 0.2 t, and we already know what t is equal to. This is going to be 27 minus 0.2. T is equal to 20, and so velocity at B is going to be, we can sort of solve this out in the calculator. 27 minus 0.2 multiplied by 20. This is going to be 23. Okay, and so we can sort of, this initial velocity is the velocity at point B, and this final velocity will be the velocity at point C. This acceleration will be whatever acceleration the car had from point B to point C. So we can start plugging these things in, and then we can find our s. So this is going to be 2 multiplied by whatever the acceleration was, and it was this thing, but the car was decelerating, so we know it's going to be negative 0.5 multiplied by s equals the final velocity at point C is going to be 0. Why? Because the car came at rest, and then minus the initial velocity squared. So the initial velocity is this guy. The velocity at point B is 23 squared. Okay, so we can now make s the subject, but before that we can sort of simplify this a bit. This is going to be 23 times 23, going to be 529, so it's going to be negative 529, and then we can sort of divide negative 529 with 2 times negative 0.5. Let's see what we get. Negative 529 divided by 2 times negative 0.5. Okay, this is going to be, wait, did I do that right? Oh yes, I did do that right. This is just going to be 529 meters. Okay, and so we sort of found this distance, 529, and we need to tell them the distance from point A to point C. So this entire distance, we're just going to add these two guys up. So A to C is just going to be equal to 2750 plus 529, and so this is just going to be plus 2750. This is equal to 3279 meters. This is the distance from A to C. So we are here with question 5, and it says one end of a light and extensible string is attached to a particle A of mass 3 kilograms. The other end of the string is attached to particle B of mass 4 kilograms. Particle A is in contact with a rough plane inclined at 30 degrees to the horizontal. Particle B is in contact with a smooth horizontal plane. A second light and extensible string is attached to B. The other end of the string is attached to particle C of mass 5 kilograms, which hangs vertically. That's a lot to take in. So essentially what they're saying is, I'm not even going to go over this what they wrote over here, but the point is there's two strings, this one that attaches AB and this one that attaches BC. And then what they've said, what the important thing to take out of all of this is that this guy is experiencing friction when it's going to move, whereas this guy will not be experiencing friction when it's going to move. The reason is because particle A is on a rough plane, particle B is on a smooth plane. Okay, and so we can move on to the next paragraph. It says both strings are taut and pass over small smooth pulleys which are fixed at the end of horizontal planes. The part of the string from A to pulley is parallel to the line of greatest slope of the inclined plane. A, B, C are in the same vertical plane. This is not useful information. Like, this is the system is released from rest in subsequent motion. C moves vertically downwards with acceleration 2 meters per second squared, and neither A nor B reach the pulley. So what they say is that they have the system in rest. They have these two strings, this guy and this guy. And then what they're saying is that obviously we know A is going to experience friction, B is not going to experience friction. They're saying when we release the system, C sort of starts to fall down. So all of this system is sort of going to go down like this. Okay, and the system has an acceleration of 2 meters per second squared. So the system has an acceleration of 2 meters per second squared. And you may be like, well, how is that the system? They're just talking about the particle C having that acceleration. Well, it's because all of this system, it's connected. So it's like whatever is going to be the acceleration of one point, since they're connected by these strings, the other point is going to have that same acceleration. And so the first part that we have to do is we have to find the tension in each string. So we got two strings, we got this guy, we got this guy. We need to find the tensions in these strings. So we can sort of find the tension starting from this point, and we can sort of go back over here and then find the tension of that second string. So what we can sort of say is we can say that BC, the tension in BC, is we can denote it by capital T, and then the tension in AB, we can denote it by small t. So if we're supposed to find the tension in BC, what you can sort of do is you can select any particle, this guy or this guy. It's completely up to you. If you select particle, I'm going to show you how to do it for both particle A and B, sorry, particle B and C. For a second, so we're trying to find the tension in string BC, right? So for now, we can ignore all of this, okay? We can sort of ignore all of this. We can sort of look at this section over here. And then what I can sort of do over here is I can sort of draw this like this. So imagine that the string is bent, right? I'm going to straighten out the string. This is particle B, this is particle C. They're both attached by strings. They're both, or you know what, I'm going to leave them bent. I feel like I'm going to just give you guys a little bit more accurate description. It's going to be like this. This is B, this is C. Now we're supposed to find the tension, right? And what you can sort of do is you can use this idea of since it's in motion over here, the system has an acceleration of 2 meters per second. We're going to use that same idea that we use in the equilibrium question. Because when forces are in equilibrium, a system is in equilibrium, it means that the resultant forces in any direction are equal to 0. In this case, when the system does have an acceleration, we can say that the resultant forces basically produce some acceleration, and according to the Newton's law, it's going to be resultant force equals mass times acceleration. So then we can sort of draw some free body diagrams over here. So C is going to experience, if I just talk about C, C is going to experience a downward force due to its weight. Its weight is just going to be mg, and then it's going to experience an upward force due to the tension in the string, which we're calling capital T. And then B will experience that same tension, but in this direction. And since they're attached by the same string, they both will experience the same tension, tension T, capital T. We're denoting it by capital T. So that T is what we're supposed to find, right? And we don't even have to look at anything else. We can sort of just remove all of this, sort of just look at particle C, and that will be sufficient enough for us to find that tension T. The way we do it is, well, we can sort of see this force, this mg, this is the force which is making C go in its direction. So it's the stronger force. Because if the tension was the stronger force, then C would not be falling down, it would be going up. So weight is the stronger force. So the resultant force is going to be the stronger force minus the weaker force. So we can convert this thing RF equals MA to the stronger force, which is mg, minus the tension equals MA. Okay, and then we sort of need to find that capital T, right? Well, we know all of this. We know the mass of C. We know what the value of G is. Then we know the mass of C, and we know the acceleration of the system. So we can sort of actually solve this out. This is just going to be the mass of C is 5 times 10, which is the value of G, or 9.81. And then minus T equals the mass of C is 5. And then the acceleration of the system is basically 2 meters per second squared. So what we can sort of see is we'll get 50 from over here. 50 minus T equals 10. We can take the 50 over there to the other side. It's going to subtract, and we're going to get this minus 40 over here. We can cancel out the negatives, and so we'll just be left with T equals 40 newtons. So that's the tension in the string BC. Now we can use the same method, and we can sort of go ahead find the tension in the string that connects A and B. So that's going to be this other string that we were ignoring. Now we can sort of look at this other string, this string, and this string is basically connecting A and B, and we were denoting its tension by small t. So if we look at particle B over here, we don't even have to look at the entire system. We can just look at particle B. Particle B is sort of something like this. It experiences a force in this direction, which is capital T, and it experiences a force in that direction, that is small t, that is the tension. So B is going to experience the tension over here, small t, and A is going to experience the tension over there, capital T. And B is being pulled to the right by the stronger tension, tension T. If small t was stronger, then B would not move right, it would move left. So small t has to be the weaker tension. And so again, we can use this idea that since B is moving to the right, and it's accelerating to the right, we know that the system is accelerating, we can say that the resultant force is equal to mass times acceleration, and then the resultant force is going to be the stronger force, force T, minus the weaker force, force small t, equals mass times acceleration. And then we can sort of solve this equation out. We can say RF equals MA, and so it's going to be capital T minus small t equals MA. Capital T is 40 newtons, we just found that out, and so minus T equals the mass of particle B, which is 4, times the acceleration of the system, which is 2, okay? And so this is going to be 40 minus T equals 8. We can take the 40 over there to the other side. It's going to subtract, and it's going to give us negative 32. We can cancel out these negatives, and then tension is going to be 32 newtons. This is the tension in the string that's connecting A and B. That's it for part A. Let's move on to part B, and they say find the coefficient of friction between A and the inclined plane. So this right over here is what we're trying to do. We're trying to find, so A is going to move in the direction of this tension T, and so friction always opposes the direction of motion, so it's obvious it's going to be in this direction. And friction is basically mu r. So what we can sort of do is we're trying to find that r, right? That's what we're trying to, we're trying to find the coefficient of friction, so we're trying to find mu. And so what we can sort of do is we can make an equation over here, and we can find out this mu. And the way we do that is we know that we can again use the same idea of Newton's second law, which is RF equals MA. So that's what we're going to do. And it's basically going to be RF equals MA So the resultant force is going to be the stronger force minus the weaker one. So it's going to be small t minus mu r equals ma. And see, we know almost all of this information. We know this acceleration of the system, it's 2. We know the mass of particle A, it's 3. And then we know we need to find mu. We know small t. Small t is basically, we just found that out, it's 32. Found that out, it's 32. And so we also know r. We can find r. I'm going to show you guys how we can find r. And so all we'll have is this u that is going to be left to find. So we're going to have an equation and just one unknown, so we can solve out for that unknown. Now, how do we find that r? I'll show you guys how we can sort of find that r. And actually, there's going to be one more thing in this equation. This is not the right equation. There's going to be one more thing in it, but where the idea is going to be the same. I'm just going to draw out the diagram we have up there over here. We have something like this. This is 30 degrees. We have the particle placed right over here. And then the particle has a tension pulling it that way, small t, has friction opposing the motion, mu r. And then it has r, which is the normal reaction. It's going to be pointing that way. That's going to be r. And then what we sort of have is we also have the weight of this particle, which is going to be acting sort of downwards like this. This is going to be the weight, mg. And then what I sort of want you guys to do over here is to sort of break this mg down into its components. Okay, break it down into its vertical component and its horizontal component. Because see, all of these forces are like straight forces, but this mg is doing something really weird. It's sort of like bending down like this at an angle. And what I want you guys to see is you can sort of form a triangle over here. If you look at that particle and that mg, what you can sort of do is you can form a triangle like this. And this angle right over here, this angle is going to be 30 degrees. So this angle is, when you're dealing with inclined planes, that angle is always the same as whatever the angle is over here. And over here, the angle is 30 degrees, so that's going to be 30 degrees as well. And so we know that this guy was mg, the weight was basically mg. This guy was mg. So this is going to be mg cosine 30. This is going to be mg sine 30. If you don't understand how I did that, you can sort of rotate this triangle out. So it's basically going to look something like this. Okay, and you know that angle is 30. You know this thing is basically equal to mg. And then you can sort of find out what this side and this side are going to equal to using some trigonometry. But yes, point is, once you sort of break it down into its components, you sort of have this mg instead of this mg, you sort of have this thing, which is going to be mg cosine of 30. And then you have the other component going in this direction. That's going to be mg sine of 30. And so what you can sort of do is, again, you can sort of make that second law of Newton. You can use that Newton's second law. You can see that this ball is going to move in that direction, right? That's the direction of motion. That's the part where it's moving. So you can say that resultant force, it's obviously accelerating in that direction due to some resultant force. That resultant force equals the mass times acceleration. And then what you can sort of do is you can say that, okay, that's the stronger force that's going to cause it to move in that direction. That's the stronger force. It's going to be t. Because see, if the mu r plus this mg sine 30, if these guys were the stronger force, then the particle would have moved down the inclined plane, not up the inclined plane. So t has to be stronger than both of these guys. So what we can sort of do is we can sort of write over here that the strong force is going to be minus the weaker forces, which is mu r and mg sine 30 equals ma. And then again, see, we know what t is, we know what m is, we know what g is, we know what sine 30 is, we can calculate that. We know what m is, the mass of particle A, we know what a is, acceleration of the system, and all we sort of don't know is we don't know this mu and we don't know this r. But we actually do know this r. Why? Because if you sort of think about it, if you think about this direction, then you can see the particle is not moving in this direction. It's not being lifted off of the inclined plane, nor is it sort of being pulled inside of the inclined plane. That means that these two forces are perfectly balancing out each other. That's why there's no movement in this direction, right? And so that basically means that r, if r is perfectly balanced with this thing, then that just means that r is just equal to mg cosine 30. And so now we actually know what r is as well. So we know all of the other terms in this problem. The only term we don't know is that mu term. And therefore, we can go ahead and we can find that mu term out because it's one equation, one unknown. So it's going to be t minus mu r minus mg sine 30. Is it mg sine 30? Yes, it's mg. Sorry, it's plus mg sine 30 plus mg sine 30 equals ma. And so this is going to be t minus mu times mg cosine 30, because that's the value of r. This is the value of r, plus mg sine 30 equals ma. So this is just going to be t minus mu times the mass of particle A. The mass of particle A was 3 kilograms. So that's 3 kilograms times g. G is going to be 10 times cosine 30 plus the mass of particle A, which is 3, times g, which is going to be 10, times sine of 30 is equal to the mass of particle A, which is 3, and the acceleration of the system, which is 2. We can sort of solve all of this out. This is going to be 3 times 10 times cosine 30. That's going to be 15 under root 3. So that's going to be 15 under root 3. Didn't write it properly. It's going to be 15 under root 3. That t, we also know this value of this small t. We found it in part A. That is 32 newtons. It's going to be 32. And then all of this is going to solve out to give us 3 times 10 times sine of 30. So that's going to be 15 plus 15. Oh, this also has a mu next to it. Don't forget the mu. This is going to be 15, and then this is going to be equal to 6. So now we essentially have 32 minus 15 under root 3 mu plus, sorry, that plus is going to change into a minus 15 equals 6. And you can sort of start solving this out over here. So that 32 and that 15 are going to cancel out. It's going to be 32 minus 15. It's going to be 17. It's going to be 17 minus 15 under root 3 mu equals 6. We can send that 17 over there to the other side. So we are going to be left with 6 minus 17. So that's going to be negative 11. and then we can sort of divide all of this to the other side. So it's going to be mu equals -11 divided by -15 under root 3. So that these cancel out, the negatives cancel out, and so mu is just going to be 11 divided by 15 under root 3, and that is going to be 0.423. So 0.423. That's going to be the coefficient of friction, and it doesn't have any units, so you don't have to put any units over there. Now we go over there to part C, and they say when the system has been in motion for 1.5 seconds, string attached to A breaks. Find the total distance that A travels up the plane from the instant that the system is released from rest to the instant that A comes to instantaneous rest. Okay, that's a lot to take in. Let me just explain you guys what they said. So I don't think I'm going to have enough room for this question, but okay, I'm going to try. This is the inclined plane, right? This is the first part of it. We have particle A, it's moving up due to that tension T. Okay, now what happens is this is from time t equals 0 to time t equals 1.5. Now what happens is in situation 2, this particle, this is now after t equals 1.5. T equals 1.5. Now what happens is you can see this particle was initially being pulled by that tension, right? It was sort of attached to a string and it was being pulled by that tension. Now when the string breaks, the tension has disappeared. Now this particle is not only experiencing friction, but it's also experiencing that component of weight mg sine theta, which was pointing downwards. It's experiencing those two forces, and it's therefore going to slow down. It's going to start slowing down. And so it's going to slow down to some final point, some final time. I don't know what it is. Let's call it TF, T final. It's going to slow down to that final point. And then what's going to happen is it's going to stop, because look, this was being pulled up. Now there's no tension, but there are those two downward forces. They're going to slow this down, slow this down, slow this down until it reaches instantaneous rest. It's going to reach that instantaneous rest. So what we're supposed to do is we're supposed to find the total distance that this particle travels from t equals 0 to that instantaneous rest situation. So how do we attempt this question? Well, we can find out this first distance, and then we can sort of do the second part, and then we can sort of add those two distances up. I'm going to do the first part down here, and it's fairly simple. We know that particle in the first situation is accelerating with an acceleration of 2 meters per second squared, and so we can simply, it's a constant acceleration problem. We can simply use the formula 2as equals v squared minus u squared, or a different formula like s equals ut plus 1 by 2 at squared. We can sort of use this, and so this is going to be the distance, and it's going to be ut plus 1 by 2 at squared. And initially the system was at rest, so this initial velocity has to be equal to 0. So this term is just going to be equal to 0. We're going to have 1 by 2 at squared, and acceleration a is 2, whereas that time t squared is 1.5. 1.5 squared. So this 2 is going to cancel out that 2, and so s is just going to be 1.5 squared. 1.5 squared. That's going to be 2.25 meters. Now this is the distance the particle covers in the first half of the situation. Now we can sort of start looking at the distance it will cover in the second half of the situation. So if we go over here to the second half, we can again use some equation to solve this out. And there's possibly two equations that we can use. One of them is 2as equals v squared minus u squared, and the other one is s equals ut plus 1 by 2 at squared. Now what I'm going to do is, you can use either one of these equations. I'm going to use this guy. Why? Because, well, I know my v. The final speed is given to me. The final speed is going to be 0. Why? Because they're talking about instantaneous rest. So that means rest means your final velocity is going to be 0. Your final speed is going to be 0. So I can directly use that information over here. Whereas for this equation, I don't know this t. I don't know the time interval. So I don't know the time interval between this 1.5 and this t final. I don't know the time interval between them. And so I cannot use this equation. I will first have to find the time interval. That just seems like a lot of work for me, so I'm not going to do that. Okay, do I know the acceleration over here? No, I don't know the acceleration. Do I know that u squared? No, but I can find that. And I can also find this acceleration. So what do I have to do? I have to find only two things in this equation. I have to find out that acceleration, and I have to find that u squared. Now, if someone chooses to go for the second equation, they have to find the u over there as well. They have to find that acceleration over there as well. And the third thing they have to find is that time interval as well. So I don't want to do that. I already know what my v squared is. It's equal to u. I can find it's equal to 0. I can find that u, and I can find that acceleration. I have to find only two things in this equation. So that's what I'm going to go with. And then I can make s the subject, and I can find the value for s. So how do I find? Let's start off with u. How do I find my initial velocity? So remember, in situation 2, when we're talking about situation 2, the initial velocity u over here is going to be whatever the final velocity v was at point 1. Because see, point 2 starts at where point 1 ends. Where scenario 1 ends, that's where point 2 starts. So the final values of point 1 sort of become the initial values of point 2. Okay, so can I find that final velocity v for point 1 for situation 1? Yes, I can do that. How do I do that? Well, I use it with the equation v equals u plus at. And I know u because, see, in situation 1, particle A started from rest. So u is simply just 0. And so my equation is just going to be a times t. Do I know my a? Yes, I know my a. It was 2. Do I know the time interval? Yes, from 0 to 1.5, the time interval is 1.5 seconds. So I can find that out. That's going to be 2 times 1.5. That's going to be 3 meters per second, 3 meters per second. And then I've basically found out this velocity, that's 3 meters per second. Because for point 2, remember, wherever point 1 ends, whatever the final values of point 1 are, those are going to be the initial values of point 2, because point 2 starts at where point 1 ends. So now I have to find that acceleration. How do I do that? Well, for that, I basically go over here to this diagram. And see, now for point 2, what's sort of happening is I don't have that tension anymore. I don't have that tension. Why do I not have that tension? Well, because the string breaks. Remember, the string breaks, and so once the string breaks, there's going to be no t. There's going to be no tension. And so the two forces that are now acting, that are now pulling this ball down, are these frictional forces and this mg sine theta, the component of weight. So these two forces are now pulling the particle down. They are the only two forces that are working to sort of pull this particle down. And so what they're going to do is they're going to decelerate it. So this particle, remember at point one, the final velocity of this particle was 3 meters per second. And so now that's going to be the initial velocity at point 2. But now those forces that are sort of acting down on this ball, they're sort of going to reduce this velocity. They're going to reduce this 3 meters per second until the point of instantaneous rest is achieved. So what they're doing is they're essentially decelerating this ball. So it's going to have some deceleration, which is going to slow it down. So we can say that resultant force equals mass times acceleration. Say Newton's second law. We're using Newton's second law in this entire problem, and that's what you want to do when you have some acceleration that's going on. So what are the resultant forces? Well, they are this guy plus this guy because they're both pointing in the same direction. So it's going to be their combined effect. So it's going to be mu r plus mg sine 30 equals whatever that deceleration is going to be, ma. So that a is what I'm looking for. Once I know that a, I can go ahead and chuck it into this equation. So how do I find a? Well, I can make a the subject over here. This is just going to be, I can send the mass over there to the other side. So a is going to be mu r plus mg sine 30 over m. Okay, that's going to be my equation for a. So now a is equal to mu r. Mu is going to be 0.423. I just found that out in the previous part. And then mu r is going to be mg cosine 30. I believe I already found out what it was. So this mg cosine 30 basically gave me this value, 15 under root 3. So it's going to be 15 under root 3 plus mg sine 30, and that I know what mg sine 30 gives me. It gives me this guy right over here, this 15 right over here. So it solves out to give me 15. So it's 15 divided by the value of mass. So the mass of this particle was, this is particle A. We're talking about particle A, and particle A had a mass of 3. Let me check if that was the mass. Yes, that's the mass. So we can sort of put this in the calculator, solve this out. This is going to be 0.423 times 15 under root 3, and then plus 15 divided by 3. Okay, so we press equal, and we get 8.66. The acceleration is 8.66 meters per second squared. And so we know the value of the acceleration now as well, 8.66 meters per second squared. But remember, we have to put a negative symbol next to this. And why do we sort of have to do that? Why do we have to do it? Because it's a deceleration. Now, they're not going to tell you that it's a deceleration. You are going to make the mistake, put a plus sign in here, and you're going to get the entire question wrong. But you have to think about the value you just found out. And going back to this example over here, I know that my particle has some velocity in this direction, 3 meters per second. These two forces are going to work to sort of remove that velocity. And so what these two forces are doing is they're producing a deceleration. They're producing a braking acceleration, a stopping acceleration. And so it's must that you put a negative sign next to it. That's really important that you don't forget that negative sign over here. Don't forget that negative sign over here. So now we have 2as. We're going to get back to that equation. We got our 2as. 2as equals v squared minus u squared. And so it's going to be 2 times negative 8.66. S is what we have to find. We know what v squared is. It's going to be 0 because at the final situation, they told us it's going to be instantaneous rest. And then u is going to be this velocity that we found out, 3 squared. And so it's going to be 2 times negative 8.66. S is equal to negative 3 times 3 is going to be 9. And make s the subject, it's going to be negative 9 divided by 2 times negative 8.66. And so s is going to be negative 9 divided by 2 times negative 8.66. Okay, so that is going to give us 0.519, or you can sort of round that off to 0.520, 0.520 meters. Okay, so you now know the distance the ball covers at stage 2. You know the distance the ball covered at stage 1. You need to give them that total distance. So you just say stage 1 plus stage 2 is equal to the total distance. That's going to be 215 plus 0.520, and you're going to get the total distance, which is going to be 2.15 plus 0.520. You're going to get your total distance, 2.67 meters. So we're about to do question number 6, and question number 6 says that a particle P moves in a straight line and passes through the point A at time t equals 0. The velocity v of P at time t seconds is given by this equation v equals whatever, and t can only be between 0 and 3 seconds. So essentially, what does all of this mathy stuff mean? This domain that you see over here is the time that it takes the entire journey. It's from 0 to 3 seconds to 3 seconds. So this is 0 second, this is 3 second, and at time t equals 0, the particle P is at point A. And so for this entire journey from time t equals 0 to time t equals 3 seconds, essentially you have this equation that you can sort of use to find out your velocity. Now, part A says find the maximum velocity of particle P in the interval t equals 0 to 3. So this is just like doing a paper 1 maximum minimum problem. This is just like simple calculus. And you can see that you sort of have an equation v equals this thing 2t plus 1, 3 by 2, so that's 3 by 2 minus 2t squared. So this is just like an equation for y equals x. Okay, you can say this v could be your y and this t could be your x. So all you're supposed to do is you're supposed to find the maxima of this equation. And so what you can do is you can first find the derivative, and with the derivative you can find the coordinates for where v is going to be maximum, for where you're going to have a stationary point. So using your derivative, using your dv by dt, what you can sort of do is you can find out your stationary points, and then you can use the double derivative d squared v over dt squared to sort of find the maximum, to sort of test the nature of those stationary points. So what we can sort of do is we can first find the dv by dt, and so we can sort of differentiate this equation. So dv by dt, and then we can differentiate these things. This is just going to be 3 by 2, 2t plus 1, so that 3 divided by 2 minus 1, that's going to be 1 by 2. Let me see if I did this correct. 3 by 2 minus 1 is 0.5. So that's going to be 1 by 2. And then we multiply all of this with the differentiation of this bracket. And so this bracket has 2t plus 1. 1 is going to differentiate to 0. 2t is just going to differentiate to 2. And then we can differentiate this thing. So this is going to be minus 4t raised to the power 1. So this 2 can sort of cancel out that 2. And so the dv by dt is simply just going to be 3 times 2t plus 1 raised to the power 1 by 2 minus 4t. So now what we're supposed to find is we're supposed to find the stationary point. We already have the equation for dv by dt. And so to find the coordinates of the stationary point, what we can sort of do is we can just put a 0 over here. And so if we put a 0 over here, then we are just going to have this equation, 1 over 1 by 2 minus 4t. And now we sort of have to solve out this equation. Now, the thing about this equation is it's a little tricky to solve, and we sort of have to do something to solve out this equation. And there is actually one thing that we can do, and that thing is to basically so what we can sort of do is we can sort of take square on both sides of the equation. So wait, this is what we can do. So we can take square on both sides of the equation, this thing squared and this entire thing squared. And so we are going to get something. Actually, you know what, I'm going to try something else. So one thing we can do, this is a tricky question. No wonder kids lose their marks. So what we can do is we can send this guy to the other side of the equation. This is going to become positive 4t equals 3 multiplied by 2t plus 1 raised to the power 2t plus 1 raised to the power 1 by 2. And this 1 by 2 is actually a square, right? So I can sort of change it and write it as, sorry, it's a square root. I can write it as 2t plus 1. Now what I can do is I can take a square on both sides of the equation. Take a square on both sides of the equation. And so what that does is that it turns this 4t into 16t squared. And over here, when I square this, it's basically going to simplify and become 3 squared multiplied by this thing squared. And so this square is going to cancel out this square root. And so I'm going to have 9 times 2t plus 1. And so now it's going to be 16t squared is equal to 2 times 9 is 18t. And then 9 times 1 is just going to be 9. And then I can sort of take all of these things to the other side of the equation. So it's going to be 16t squared minus 18t minus 9 equals 0. Okay, and then what I can sort of do is I can basically apply middle term break on this. I can apply the quadratic formula on this. And personally, I'm just going to go with the quadratic formula. So this is going to be minus b plus minus b squared. So that's negative 18 squared minus 4ac. 4ac, a is 16. This is 4ac over 2a. This is 2 times 16. And then we can solve this out, and we're going to get two values for t. So we can sort of do that. So this is going to be 18 plus under root negative 18 squared minus 4 times 16 times minus 9 divided by 2 times 16. Okay, so we press equal, and we get 3 by 2. We get 1.5 seconds as our answer. And then we sort of, when we change the sign over there to negative, we get our other answer, change it to negative, and we get negative 3 by 8. So we get negative, this is going to be 0.375 seconds. Now, which one do we have to go for? Well, we have to go for this guy right over here. And the reason for that is because if you go to the start of the problem, you are only allowed positive values from 0 to 3, and time cannot be negative. So you cannot use that other value of time. So now this is your t, it's 1.5, and so what you're trying to see is you're trying to check out the nature of this point. And so it's, well, I mean, it has to be maximum. There's like no other option. It has to be maximum. There's only one stationary point. There's only one stationary point, because this guy is out of the problem, right? So this is the only stationary point, and in the question they ask you to find out the maximum velocity. So obviously, if there's one stationary point, then this just has to be where we will have our maximum velocity. So this has to be a maximum, because otherwise, why would they say find the maximum velocity? Okay, so this stationary point, this is going to this station, at this stationary point, we will have our maximum velocity. And so what we can sort of do is we can go back to our equation, v equals 2t plus 1, 2t plus 1 raised to the power 3 by 2, and then we have minus 2t squared, minus 2t squared. And so what we can do is now we know the value for t, we just got to put it in here. V equals 2 multiplied by 1.5 plus 1 raised to the power 3 by 2 minus 2, 1.5 squared. And we can solve this out, and our maximum velocity is going to be, so it's 2 times 1.5 plus 1 raised to the power 3 by 2, and then it's going to be minus 2 times 1.5 squared. So this is going to be equal to 3.5 meters per second. That's the maximum value of the velocity, 3.5 meters per second. Okay, moving on to part B, they say it is given that the interval 0 to 3, the velocity p is always positive. So what we're supposed to do is we're supposed to find the distance of p from A at the instant when p is moving at this maximum velocity. So I guess they're talking about this maximum velocity. And what we're supposed to sort of do is, remember, we talked about this thing where we had our time t equals 0, and then our time, the maximum our time can be is time t equals 3 seconds. And so this is where our maximum velocity is. It's at the time t equals 1.5 seconds. So right in the middle, 1.5 seconds. This is our max velocity. And for at this time, when we're at this time, when the particle is at this point in the journey at 1.5 seconds, that's when they want to sort of ask this question of, okay, tell us how far is the particle away from A, or how much distance has the particle covered for these 1.5 seconds. That's what the question says. So what we can sort of do is, and in a different way, I can sort of draw out a graph over here. And I can sort of imagine, let's say, imagine a curve, something like this, okay, or maybe something like sort of like this. Okay, and so what they're asking, let's say this is the maximum velocity, and this maximum velocity is at time 1.5 seconds. So this is the time axis, that is the velocity axis. And so when we started from A has to be our starting point. So this is A. And now when they're asking for this distance of the particle p from A at this instant where we have our maximum velocity, what they're sort of asking for is they're sort of asking for this area under the graph. And I don't know if the graph looks like this or if it has any other shape. I don't know the exact shape of the graph. I'm just assuming this shape and explaining it to you guys what they're actually asking for. And so we know how to find this area. We know that we can sort of integrate this stuff and we can find that area. And we already know that the curve equation is v equals 2t plus 1 raised to the power 3 by 2 minus 2t squared. I'm just going to check that one more time to make sure this is what I'm talking about. 2t plus 1 3 by 2 minus 2t squared, yes. So this is the curve equation. And what I'm supposed to do is I'm supposed to find the area under the curve from t equals 0 to t equals 1.5. So all I'm supposed to do is I'm supposed to integrate from t equals 0 to t equals 1.5. And that's my curve up there. So that is 2t plus 1 raised to the power 3 by 2 minus 2t squared dt. That's what I'm supposed to do. I'm supposed to integrate this thing. So it's really simple. What we can sort of do is we can sort of integrate this guy and we can integrate this guy. And what I can sort of do over here is I can sort of make two different integrals. You can make a sort of like these two different integrals. It's 2t plus 1 raised to the power 3 by 2 dt minus and 2t squared dt. Okay, and then I can sort of integrate them and find out what this part is going to be and what this part is going to be, and then I can apply the limits onto them. So you can technically integrate this in whatever way you've learned integration. I'm going to apply the way in which I've learned integration. So what I can sort of do is I can sort of say this inner function is basically equal to u, and so u is equal to 2t plus 1. And so what I can sort of, I'm basically applying the u substitution over here. If you want to learn this, then you can sort of check out my playlist, my integration playlist. It's either going to be u substitution in AS level playlist or in A level playlist, which is for P3. But you can check out those playlists. You'll find the video for u substitution. Then what we can sort of do is we can sort of differentiate du by dt, and we just find out that the answer is 2. And so we need to make dt the subject, and so we can do that. And so dt is just going to be 1 by 2 du. Okay, and then I could basically put that in this integral. I can say this integral is basically u raised to the power 3 by 2, and the dt, I can replace it with this thing, going to be multiplied by, I'll actually use a dot sign because multiplication can be mixed with the x variable. I'll just use this instead. And so you can see this is a constant, so I can take this constant outside the integral. I can take this constant outside the integral. It's going to be 1 by 2. And I have a constant over here as well, so I can take that too outside of the integral. Okay, and then now I can just integrate this thing. So this u raised to the power 3 by 2, it's just going to be 3 by 2 plus 1. So that's going to be 2.5. That's going to be this. All of this is going to integrate to u raised to the power 2.5 divided by 2.5 multiplied by this 1 by 2. And then from over this part, what we can sort of get is this t squared is going to become t to the power 3 divided by 3. And so we can simplify this. We're going to have 3 cubed, 2t cubed divided by 3. And we can simplify this part over there as well. Wait, hold on. So this is going to be 2 times 2.5. That's just going to be 5. So this is going to be u raised to the power 2.5 divided by 5. And I know what u was, so u was basically equal to this thing, 2t plus 1. So I can replace u with 2t plus 1 raised to the power 2.5. And so now I've integrated this entire thing, and now what I can sort of do is I can go ahead and apply limits onto this thing, and the limits are 1.5 and 0. Okay, so let's do that. So for 1.5, let's apply the 1.5 limits over here. So this 2t plus 1 is just going to become 2 multiplied by 1.5 plus 1 raised to the power 2.5 over 5. So did I get that correct? 2t plus 1 raised to the power 2.5. The t is going to be replaced with 1.5, and then minus 2 times 1.5 raised to the power 3 divided by 3, and then minus 2 times 0 plus 1 raised to the power 2.5 over 5, and the next term is just going to be 0. So this term is just going to become 0 because anything multiplied by 0 just becomes 0. So we don't have to write that term out. And this thing. So this thing is going to simplify. So that 2 times 0 is just going to be 0. So we can sort of erase this term. So it's just 1 raised to the power 2.5, which is just going to be 1 by 5. So this entire thing is just going to simplify to 1 by 5. And then we can sort of do the other bit, which is 2 times 1. Wait, I have to double bracket this. 2 times 1.5 plus 1 raised to the power 2.5. And then we divide this by 5. And then we subtract from it 2 times 1.5 cubed divided by 3. So that is going to be 83 by 20. 83 by 20 minus 1 by 5. And so 83 by 20 minus 1 by 5 is going to give us 3.95 meters. So the distance covered is going to be 3.95 meters. Now, before moving to question 7, I'd actually like to explain something I did over here in part A of question 6, and that is this step right over here. Why did I sort of square these things? Well, the reason for that is because, look, if I had all of this stuff, right? All of this stuff, right? And in the step before that, I sort of had this thing. Now, see, this is an equation that has the variable t over there in the bracket and t over there in the bracket. Now, how will you expand this bracket, right? How do you expand this guy? How do you expand? Because you need to get that t out of that bracket to make it the subject and do something with it, or find its value. So this t is already outside of the bracket. How do you get that t outside of the bracket? Or in other words, that t is that power of 1 by 2 basically means it has a square root. How do you get that t outside of that square root? You don't know how to do that, right? So we need to somehow figure out a way to get that t outside of that square root, outside of that bracket. We need to sort of do something about it. And so one thing I did was I basically took this, and so basically one thing that cancels out the square root, or one thing that finishes a square root, is taking the square of a square root. That basically cancels out the square root. And so for that, what I did was I sort of took this 4t to the other side, this guy to the other side of the equation over here, and then I can technically do anything to the equation I want as long as I do it on both sides of the equation. So that's why what I did was I took a square over here, because then I knew the square would sort of cancel out that square root. And then, but if I take a square on this side, I also have to take a square on this side as well. So that's essentially what I did in this step, and I felt like I should go ahead and explain that. So moving on to question 7, it says a particle p of mass 3 kilograms is projected with a speed of 8 meters per second up the line of greatest slope on a rough plane. Rough plane means there will be friction, not a smooth plane. Inclined at 30 degrees to the horizontal. P is projected from point A on the plane and comes to instantaneous rest at point B on the plane. P then slides back down the plane. The coefficient of friction between P and the plane is this guy. So the coefficient of friction basically means mu, and so they basically just told us the value for mu is this thing. Using an energy method throughout, so throughout means the entire problem, I have to use an energy method. Find the speed of P at the instant it returns to A. The speed of P. Okay, so let me just explain what's happening in the question. And the question basically has two parts. I'm choosing a good color over here, so this is the first part. So we have an inclined plane, okay? And then we start over here at point A, and let's say then we have a point B over here on the inclined plane. So what happens is that at point A we project a particle P. This particle is called particle P. And remember, this inclined plane has an angle of 30 degrees. 30 degrees. So we project this particle P, and it has a velocity of 8 meters per second. And what happens is at point A, when we project it, it has a velocity of 8 meters per second. When it goes to point B, it basically stops. This is point B. It basically stops. Instantaneous rest, that's what it means. And so it has a velocity of 0 meters per second. That's the first part. Now, in the second part, we still have our A, we still have our B. But now what's going to happen is that the particle is going to fall down. So the particle falls down, back down, Okay, and what they're saying, so this is still B, this is still point A. What they're saying is that this particle is going to fall down from point B all the way back to point A, and what we sort of have to do is we have to sort of tell them the final velocity v at this point A. So we can put a tiny a over here to say we have to tell them the velocity at point A when it falls back down to that point. And of course there is friction involved. So how do we use an energy method to solve out this problem? It's really easy. You can imagine, so I'm going to use some different colors for energy just so we can do this problem, properly. Let me just see if pink looks okay. Okay, yeah, pink looks okay, but I'm going to instead use, how does this look? Okay, that looks okay too. So kinetic energy is with this color, and then friction is with red, or actually I can use orange. So that's for friction, and then for gravitational potential energy, GPE, we're going to use blue. And so initially, when we at scenario one, when we're projecting scenario one, when we're sort of projecting this particle P from point A and giving it that initial velocity of 8 meters per second, it has no energy other than the kinetic energy Ke. So it has nothing but Ke. So that's an energy, that's a bank. You can sort of understand it as a battery. So we have a battery full of Ke. Now what happens is at the end of this part one, when the particle P is going to go all the way up to point B, its kinetic energy is going to be depleted. It's going to convert into friction. It's going to do some work against friction, obviously. So some of it is going to go to friction, which is lost energy. So this is lost. And then some of it is going to go to some, using blue for GP, some of it is going to go to GPE. Why? Because it gained some height, GPE. This is the height it gains. This is the height it gains. Okay, so the vertical height it gains, this one in blue, this vertical height in blue, this is going to be the height it gains, and due to that height, what's going to happen is it's going to have some gravitational potential energy. So now, at the scenario 2, this particle is at point B, it's at rest over there. It only has one sort of energy, that's gravitational potential energy. It doesn't have any kinetic energy because it's not moving, it's at rest. And that energy that was lost due to friction, you cannot recover that. So now, in its bank, it only has GPE. We have a GPE battery. And this GPE, as this ball sort of starts to fall down, this particle sort of starts to fall down, we're going to have energy that is going to be converted into kinetic energy, because obviously the ball is going to get some speed, some kinetic energy. And then again, this time we will have friction, but in the opposite direction now. We will have friction, some energy will be lost friction. This is lost energy. So when we are sort of going up, the friction is in this direction. When we are falling down, the friction is in that direction. So friction opposes motion. So this is what the energy bank looks like in this situation. So first thing I'd like to sort of do right off the bat is to find that height. Okay, let's first go ahead and find that height. And the way we can sort of do that is, okay, so this is a tricky problem. Okay, so there is a way we can find height. So we want to find this height. We want to find this height, okay, this blue height. And we can use some equations of motion to find this height because we're not given any information. And so we won't be able to find that height. But we can't really do that, can we? Because we're not allowed to sort of use the equations of motion. They said throughout the problem, clearly stated that throughout the problem, we sort of need to use an energy method. Okay, so okay, one thing we do know is if you look at part one, is if we talk about part one, what we know is the change in kinetic energy is, or actually, I'm going to do this in one color so it's consistent. So we know that for part one, the change in kinetic energy is equal to the change in friction plus the change in gravitational potential energy, because the kinetic energy is changing into these two energies. Okay, and since the kinetic energy is equal to 1/2 mv squared, we can sort of find this 1/2 mv squared because we have all of this information. We have m, we have v, so we can sort of find this guy. And then friction is basically going to be force times distance, right? That's what friction is going to be. It's going to be mu r, which is the frictional force times whatever the distance is, times whatever the distance is, times whatever the distance. So the distance of what? The distance of this plane. Why? Because as this ball, this particle P sort of moves onto that plane, friction is going to be in the opposite direction. And what is the value of friction? The value of friction is mu r. So it's like, what is the work done? The work done against friction, the work done against friction, let's call it F. What is this equal to? What is the formula of work done? It's F times distance d. Okay, so essentially this F, since this is frictional force, it's going to be mu r, and this distance is the distance of that plane, because as it's going up, it's covering distance along that plane. So simply put, this is going to be mu r. This is going to be mu r times that distance d of the inclined plane plus, so this is the formula of work done against friction. And so the GPE is just going to be mgh. So this distance is d and this height is h. So that's mgh. Now, what we sort of need to do is we need to find that height and we need to find that distance d. Those are really important to us as of now. And so we are given mu. We do know mu. We can find r. Yes, we can find r. We don't have d. And we do know, so what we don't have, I'm going to circle it. We don't have d. And we do have m, we do know g, we don't have h, we do have m, and we do have v. So we have one equation and two unknowns, but we're trying to find that height because see, that height is really important to us. Once we can find that height, we can sort of like in the second step, what we're going to do is we're basically going to have some height over here. See, the GPE is due to that height, so that's why that height is really important to us. If in the second step we're going to apply mgh over here, so we will need that height, and then what we will do is basically we will say that this mgh is equal to kinetic energy 1 by 2 mv squared plus the work done in friction. So mu r plus mu r multiplied by the distance. So this friction is going to stay the same in both cases because it's the same inclined plane. We're going to have to do the same amount of work done. Okay, so it's the friction is going to stay the same in both the cases, but we will sort of need this height to find this kinetic energy. So how can we sort of do that? And then one thing we can sort of do is we can sort of relate d and h. Why? Because we are given a triangle. This inclined plane is essentially a triangle. And so we can actually relate these two quantities in a way that we can get d in terms of h, and then we will only have one equation and one unknown. So what I'm trying to say is basically if I draw a triangle sort of like this, so this was 30 degrees, remember? And so if we have this distance as d, and we have this height as h, then we can sort of use this angle, this guy, and this guy to link all of these quantities together and get an equation for d in terms of h. So we can use sine 30 is equal to, so sine is equal to perpendicular over hypotenuse. The perpendicular is small h, and the hypotenuse is d. So if we make d the subject, we are going to get d is equal to h over sine 30. So that's really useful to us. This equation is really useful to us because now we can sort of just put h over sine 30 over here, h over sine 30. And now we have one equation and one unknown. The h is the only unknown in this equation. It does not have another variable. So we can solve this equation. So this thing, this d, we can sort of write over here that d is equal to, right somewhere over here, that d is equal to h by sine 30. So that's useful information for us. Okay, and then one thing that we can sort of do is we can also find r. So you guys may be like, well, we don't have r, but no, we actually do have r. The way we find r, I'm just going to erase this, is by using Newton's second law. We can erase this. We don't really need this guy. Imagine a particle over here, right? That particle is going to have some weight. Okay, let's call it mg, and then it's going to have some normal reaction force, which is going to be in that direction. Normal reaction is going to be in that direction. Why? Because normal reaction is perpendicular to the plane. So this normal reaction is basically at 90 degrees to the plane. So that's r. And you can sort of see that there's sort of no movement up or down of this particle p. It's not being lifted off of that inclined plane, nor is it being pushed inside of the inclined plane. It's just on the inclined plane. So that means that this component, if I draw a triangle over here, this component of mg, this component, it's basically this angle is 30, so this angle has to be 30 as well. And so this is just going to be mg cosine 30. So this mg cosine 30, this component of the weight, this mg cosine 30, it's perfectly balanced with that normal reaction r. If one of those things were not balanced, then if r was way too much, then the particle would have been lifted off the plane. If mg cosine 30 was too much, the particle would be pushed inside of the plane. So, but it's not happening right over here. So that means that they must be perfectly balanced, and r equals mg cosine 30. r equals mg cosine of 30. Okay, so this is the first equation, and then d equals h over sine 30 is the other equation. And so what we can sort of do is now we know all of these things, we can actually find our height h. Now we got 1 by 2. Mass of the particle is, I believe, 3 kilograms. So this guy is 3. The velocity was 8. Got 8 squared. And so we got mu, as they gave us mu in the question. It's 1 by 12 over under root 3. So that's just going to be under root 3 by 12 times r. And we know what r is. R is just mg cosine 30. So that's 3 times 10 times cosine 30. And then times h over sine 30. And then all of this is going to be added into mg. So that's 3 times 10 times that height h. So we can sort of start to simplify this out. We can sort of first simplify the kinetic energy. It's going to be 0.5 times 3 times h squared. It's going to be 96 is equal to, we can sort of simplify all of this. So under root 3 over 12 multiplied by 3 times 10 times cosine 30. All of this, that's 15 by 4, and then multiplied by 1 over sine 30. So this is going to be 15 by 2h. All of this is going to be 15 by 2h. Okay, 15 by 2h, and then that's just going to be 30h. So both of these terms have h. What I can sort of do is I can say 96 is equal to h, 15 by 2 plus 30. And so this is going to be 96 is equal to h. So 15 by 2 plus 30. That's going to be 75 by 2. So h is being multiplied with 75 by 2. Now we can send the 75 by 2 over there to the other side, and it's being multiplied with h. So when it goes over there, it's going to sort of divide with 96. So 96 divided by our answer, which is 75 by 2. And we are going to get 64 over 25, which is also the height is equal to 2.56 meters. So that's our height. That's the h. And now what we can do is we can sort of find d as well, because d was simply h by sine 30. So we can say 2.56 divided by sine 30. Sine 30. That's going to be 5.12 meters. Okay. Now what we can do is we can sort of find the work done against friction, and we can find the gravitational potential energy, the change in gravitational potential energy as well. So the work done against friction is just going to be mu r times d. So it's going to be mu rd, and that's going to be equal to mu is, we know what mu was. It was equal to under root 3 by 12. We know what the normal reaction r is. It's mg cosine 30. So that's m times g times cosine 30. And then we know what d is. D is just 5.12. So all of this is just going to be 19.2 joules. 19.2 joules. And why is it joules? Because work done in energy is in joules. It's going to be 19.2 joules. And then we can sort of find the GPE gained, because as you gain some height, as you ascend to a height, you gain some gravitational potential energy. That's just common sense. So that's going to be mgh. So that's going to be 3 times 10 times the height h, which is 2.56, and that's going to be 76.8 joules. Now this thing is going to stay the same. It doesn't matter if you're going up the inclined plane or if you're going down the inclined plane. And the reason for that is because your mu stays the same, your r stays the same, and your d will stay the same, because from A to B, if the distance is 5.12, then from B to A, the distance will be 5.12 as well. R doesn't change because that's your normal reaction. So mg cosine 30, which is the downwards component of weight, is going to be the same as whatever r is, and the downwards component of weight is not going to change because the particle's weight is not going to be changing, its mass, it's not going to be changing. So it just makes sense that r wouldn't change. And mu doesn't change because mu depends on the surface of a plane. So if it's the same plane, the surface is not changing. So 19.2 is going to stay the same. Doesn't matter if you're going up or if you're coming down. Now this mgh, this thing is going to be, so now we're on step 2, right? This was step 1. So that we know that our energy converted into friction, that's 19.2 joules, and this guy was 76.8 joules, the energy that was converted into gravitational potential energy. So this battery now has 76.8, and this lost energy is 19.2. So now in the second situation over here, in the second case, we are basically going to be starting off with 76.8 joules. And now we are going to have some lost energy, which is going to be the exact same as in the first scenario. Remember? It's going to be 19.2 joules. That lost energy is going to be the same. I've just explained the reason. So that means that we can subtract this amount from this amount, and the remaining amount is going to be for this kinetic energy. So let's find that remaining amount out. That is going to be 76.8 joules minus 19.2 joules. And that's just going to be 26.8 minus 19.2. This is going to be 57.6. Now this amount of energy is going into the kinetic energy bank. And so if this is going to be the change in kinetic energy, then we can simply say that the change in kinetic energy is equal to 1 by 2 mv squared. So this is just going to be 57.6 equals 1 by 2 times the mass, which is 3, and v squared. So we can find the v squared, therefore, and this is just going to be 57.6 equals 3 by 2 times v squared. So this 3 by 2 is being multiplied to v. So when we send it over there to the other side, it's going to divide 57.6. So we can just say 57.6 divided by 3 by 2. And so this is going to be 38.4. 38.4 equals v squared. And so what we can do is we can just take the square root over here, 38.4. And so the velocity is going to be, so we can square root our answer, and our velocity is going to be 6.1. We can sort of say it's 6.20. We can round this off to 6.20 meters per second. And you can see when you were sort of going up on the inclined plane, right, your energy over here, you had a velocity of 8 meters per second. So your velocity over here, when you went all the way up over here, your velocity over here was 0. So what happened was you basically lost some energy to friction. And that's why when you sort of come down to point A, this time your velocity, you will not get the same velocity back. You will not get that same 8 meters per second back. Because now going up on your way, you lost some energy to friction. Coming down on your way, you lost some energy to friction as well. So that's why your velocity is less than, so this thing is less than what you initially started off with.